Welcome, focused learners, to today's explainer. If you've ever felt like training a neural network is just some kind of dark art, trust me, you are absolutely not alone. There's this massive and honestly quite frustrating gap between understanding how a basic convolutional layer works on paper and actually getting your model to hit state-of-the-art results in the real world. So today, we're going to completely demystify that entire process. We're drawing entirely from the incredible insights of Andrej Karpathy to give you a meticulous, battle-tested methodology for building and training neural nets. Okay, let's dive into this.
Here's the menu for today's masterclass. First up, we'll tackle the plug-and-play myth. Then, step 1, become the data. After that, step 2, build the skeleton. Then we'll get into overfitting and regularizing, and finally, tuning and squeezing that last bit of juice.
All right, section 1, the plug-and-play myth. A common illusion. Let's start by totally shattering this idea.
Now, what's really interesting about this is the trap that so many beginners fall right into. A lot of libraries and frameworks take real pride in showing off these 30-line miracle snippets of code, and it gives this completely false impression that this stuff is just plug and play. Because we're so used to clean APIs and standard software engineering, we kind of expect deep learning to be the exact same way. Just drop in a miracle snippet and boom, data problem solved. But as Karpathy points out, neural networks are a leaky abstraction. They are absolutely not an off-the-shelf technology. Things like backpropagation, batch normalization, optimizers, they don't just magically work without you really understanding what's going on under the hood.
And honestly, this is where the real pain begins. In standard software development, if you plug in an integer instead of a string, what happens? The code throws a massive, loud exception. It fails fast, right? You fix it and move on. But neural networks? They fail silently. Literally everything might be syntactically perfectly fine, but logically completely flawed. Like, let's say you forget to flip your labels when you horizontally flip an image during data augmentation. The network isn't going to crash. No, it'll just internally learn to detect flipped images and silently flip its own predictions. Or, say you tried to clip your gradients, but accidentally clipped the loss instead. The code still runs, it just works worse. Taking a fast and furious approach here? It's basically just a guarantee that you're going to suffer.
So what's the cure to those silent failures? Well, it's a mix of extreme patience, a healthy dose of paranoia, and a highly defensive methodology. Here's our 6-step recipe to completely eliminate unverified complexity. We're going to build from simple to complex, and we are validating every single hypothesis along the way.
Moving on to section 2. Step 1, become the data. And spoiler alert, don't touch any code yet. This is the absolute crucial prep work for our recipe. You actually need to spend hours literally just looking at your data. Seriously, don't write a single line of code yet. Your brain is a fantastic tool for this. By just visually scanning thousands of examples, you're going to uncover things like duplicate images, corrupted labels, weird data imbalances. You've got to ask yourself these essential questions. Are local features enough to make a classification, or do we need global context? How noisy are the labels? Are there duplicates? What kind of variation is just spurious? How far can we actually downsample without losing the core info? Look, sorting, filtering, and just visualizing outliers at this stage, that's going to save you weeks of debugging a model that was frankly doomed by bad data from the very start.
Okay, section 3, step 2, build the skeleton. Now that we're basically one with our data, we systematically set up our end-to-end training and evaluation pipeline to really gain trust in its exact functionality.
And this brilliantly illustrates exactly how we build that trust. We use what we call dumb baselines. First, you want to get a human baseline. Literally evaluate your own human accuracy on the dataset so you have a real interpretable metric to compare against. Next, train an input-independent baseline by literally setting all your inputs to 0. Think about it. The model should perform horribly. If it doesn't, well, your model isn't actually learning to extract information from the input at all. Finally, take just 2 or 3 examples and overfit that single batch. Make sure your model has the capacity to reach exactly 0 loss. If it can't even do that, you've got a fundamental bug in your setup and you simply cannot move forward until it's fixed.
During this whole skeleton phase, you've got to adopt this overarching, kind of funny mantra, don't be a hero. Seriously, resist the temptation to get incredibly creative stacking crazy architectural Lego blocks. Just copy-paste a proven simple architecture. If you're doing images, grab a ResNet 50 and call it a day. Disable all unnecessary fanciness, turn off data augmentation completely for now, and above all else, absolutely fix your random seed. You need to guarantee that running the code twice gives the exact same outcome, otherwise you're going to lose your mind while hunting for bugs.
Now, here is an incredibly powerful pro tip straight from the source material and the community surrounding it. Vectorized and broadcasted operations are notoriously sneaky for silently mixing information across the batch dimension. To catch this, you need to chart your dependencies. Try setting your loss to be something trivial, like just the sum of all outputs for, say, example I. Then run your backward pass. You absolutely must ensure that you get a non-zero gradient only on the ith input. If any other inputs suddenly have gradients, your batches are leaking into each other and you've got a bug to squash.
All right, Section 4, overfit and regularize. Two distinct phases. Let's move into the actual cooking process. The biggest thing to remember here is that you cannot do both of these at the same time. They are two distinct, sequential phases of training. First up, our goal is to prove the model can actually fit the data. That's the overfit phase. We use a large model, focus entirely on driving down that training loss, and use a safe optimizer like Atom at a learning rate of 3e-4. Oh, and crucially, do not trust default learning rate decays. Depending on your dataset size, they might drive your learning rate to 0 way too early. Now, once, and strictly only once we are successfully overfitting, we shift gears. We start to regularize. This is where we willingly sacrifice a little bit of that training accuracy to pull the model in and improve our real-world validation loss.
So how exactly do we regularize? Let's look at this hierarchy of tactics. The absolute best, gold standard way to regularize is simply get more real data. It's the only guaranteed way to monotonically improve performance almost indefinitely. Seriously, stop trying to squeeze juice out of a tiny dataset if you can just go collect more images. But okay, if you can't, use half-fake data through aggressive data augmentation. You can also try decreasing your batch size, which actually provides stronger regularization because the batch statistics kind of wiggle around a lot more. Add spatial dropout, employ early stopping to catch the model right before it overfits, and whenever possible, always leverage a pre-trained network. Finally, we reach the plating and garnishing stage. Section 5, tune and squeeze juice. This is where we optimize our hyperparameters and eke out those final performance gains. When it comes to tuning, you really want to choose random search over grid search. Why? Because neural networks are very often much more sensitive to certain parameters than others. Think about it. If parameter A matters a ton, but parameter B doesn't matter at all, a grid search is just wasting your time checking B at all these fixed intervals. Random search is vastly superior because it samples the truly important parameters much more thoroughly across that whole high-dimensional space.
And of course, we have to share this incredibly tasteful piece of humor derived directly from the article and the community. The state-of-the-art approach to exploring a nice and wide space of models and hyperparameters is to use an intern, also known as grad student descent. It's funny, but it really highlights just how grueling and empirical this final tuning phase actually is. Sure, there are fancy Bayesian optimization toolboxes out there, but a lot of the time, it really just comes down to someone meticulously running endless experiments to find that absolute perfect configuration.
Now, once you've found your best architecture and hyperparameters, there's a nearly guaranteed trick to squeeze out the very last drop of performance: model ensembles. Simply training multiple models and averaging out their predictions will almost always buy you a free 2% of accuracy across the board. So hey, if you can afford the extra computation at test time, definitely do it. And lastly, don't forget to just let it bake. It's so tempting to stop training when the validation loss looks like it's leveling off. But neural networks keep learning for an unintuitively long time. Karpathy actually shares a fantastic personal anecdote about this. He once accidentally left a model training on a server right before leaving for winter break. When he finally returned in January and checked on it, he found that simply by letting it bake for that long, the model had organically achieved state-of-the-art results. Unbelievable, right?
So the crucial point is this. Success in deep learning isn't about finding some magic 30-line snippet of code. It's about extreme patience, a healthy amount of paranoia, and a meticulous, step-by-step culinary process. From truly becoming one with your data to building those dumb baselines and completely separating your overfitting phase from your regularization phase. If you apply this exact recipe to your workflow, you'll stop suffering from those agonizing silent failures and start cooking up truly robust, state-of-the-art models. So before you write another line of training code tomorrow, ask yourself, are you actually cooking, or are you just throwing ingredients at a wall and hoping they stick?